do section 6.2 in our textbook, but I broke this into two parts, so today we'll just talk about what's called the natural number. So far in your math career, you've learned two special numbers. That first number is pi, which is obviously a geometry number. And this year you've learned the properties of I, such I is the square root of -1, and you learned how to work with the letter I. So now it would be time to introduce a new number, as it's going to come up in our logarithmic problems. So this gentleman right here, this is Jacob Bernoulli. He was a Swiss mathematician back in the 1600s, and he was interested in what's called compound interest. So if you're not familiar, when you put money into a savings account, the bank pays you a certain percentage of that money, and that's known as interest. It's very, very low, but it's something. So he was interested in how that worked out, so he started investigating. So we'll consider a very simple scenario. Let's say that you open a bank account, you put $1 into your account, and your bank is very generous and they give you 100% interest each year. Now, that will never happen in your life. Usually banks will pay you about 0.06% interest. That's how low it is. But let's say this bank is super nice. So if I do a timeline, and I go from time 0 all the way to 1 year. So there's my timeline for the whole year, and I put $1 into my account. Well, at the end of the year, I should have $2 in my account because I already had $1, and then the bank's going to pay me 100% of the dollar I started with. So I have $2 in my account. However, this really isn't how growth works, especially if you consider other applications like, for example, you growing. At one point in your life, you were probably a foot tall, and you obviously surpassed 2 feet at some point, but it's not like you woke up one day and you were magically 2 feet taller. That happened over time, and Bernoulli knew that, so he started looking at it in a different perspective. So instead of seeing 100% in a whole year, what if you just focused on, say, 6 months of a year? So for example, if you have 0, 6 months, and a year, and you want to make, the bank's going to give you 100%, but they're not going to do it all at once, maybe they'll give you 50% for the first half of the year and 50% for the second half of the year. So same scenario as before where you start with $1. However, at 6 months, the bank's going to obviously pay you. You're going to have your dollar you started with, and the bank's going to pay you 50% of your dollar. So that would give you $1.50. So at 6 months, that's what's sitting in your bank account. And then what happens is the rest of the 6 months, the bank's going to pay you again. So this time you have $1.50 currently in your account, and the bank's going to pay you 50% of your $1.50, which would give you $2.25. You made more money. You made a quarter more. So then Bernoulli said, well, let's keep going. Let's try getting paid 4 times a year. So if you're getting paid 4 times a year or getting paid quarterly, that would mean every 3rd month you're getting money. So there's 4 intervals, 1, 2, 3, 4. But the bank's not going to pay you 50% each interval. That wouldn't make 100%. So what they're going to do is they're going to pay you 25% for each interval. So we're still going to start with $1, but this time, by the end of month 3, the bank will pay you $1 plus 25% of that dollar, which would give you $1.25. So you have $1.25 in your account at 3 months. And then we're going to do it again. So 3 months later, you had $1.25 in your account, and the bank's going to pay you 25% of that $1.25, which roughly puts about $1.56 in your account. And the bank's going to keep doing that. So at 9 months, you have $1.95, and at the end of the year, you have $2.44. So what happened was we started with the first scenario, which left us with $2. The second scenario left us with $2.25, and now this third scenario, we have $2.44. So Bernoulli saw a pattern emerging. He's like, you're getting more money every time this happens, so let's try to make a table and try to analyze this data. So he decided to let n equal the number of times basically the bank's going to put interest into your account. So we would call that compounded. And if it's once a year, that's annually. So at the end of 1 year, he had $2 in the account. Bernoulli was able to fashion that too into this formula, and you'll see why he's doing that in a second. So when we did it every 6 months, that's called semi-annually, semi being half of a year, you ended up with $2.25 in the account. And he fashioned that as the formula for $2.25. So if you type this in a calculator, you're going to get $2.25. So he was taking this information and he was making it into an exponential formula. All right, when we got paid quarterly, we ended up with $2.44, which can be fashioned as that formula. And then what if you got paid monthly? So that would be 12 times a year. That would roughly leave you with $2.61 in your account. And you could fashion this formula. So the idea is you're supposed to see a pattern emerging from the formula. All right, so what if you got paid daily? You would end up, if you use Bernoulli's formula, you would end up with $2.71. So Bernoulli saw what was going on, and he saw a pattern that every time n was increased, or every time you got paid more intervals, you ended up having more money. So he posed the question, like, what if n just kept on growing forever? So what if the bank paid you every hour? What if they paid you every second? What if they paid you every half a second? So you would take your year and divide it up into that many intervals, and it just keeps getting to be more and more and more intervals. So you're generating more interest more quickly. So in calculus, there's a way to show this situation using what's called a limit. So you write LIM, that's short for limit, and then you pronounce this as n approaches infinity. So you would say the limit as n approaches infinity of, and here's that formula that he was using to quickly get those numbers. So in this formula, n would stand for the number of times basically you're getting paid in a year. So if it was compounded quarterly, the n would be 4, both here and here. So his question was, let's pretend you could plug in the number infinity for n. What would that value be? What would you get? So what's the maximum money you can make in that account? Well, it's kind of a trick question because it's exponential. It's just going to keep growing. So in the banking world, this is called continuous interest because it keeps on growing and growing and growing and growing, and you can keep dividing those intervals up and making more and more intervals. Bernoulli was dying to know this. He knew that the number he sought was somewhere between 2 and 3, but he couldn't actually figure out that final number, or at least get a better idea of that final number. That's okay though, because 50 years later, a mathematician named Leonhard Euler was able to figure it out. So he actually was able to compute the number 2.7182818 and so on up to 23 decimal places. Now obviously he's not going to keep writing all those digits, so he just assigned a letter to that specific number, which we know today as E. So just like pi is symbolic for 3.1415 ... E is symbolic for this interest number that seems to keep coming up and getting a little bigger every time. So E is actually called Euler's number because he's the one that's credited with its discovery. It's also referred to as the natural base, which is what we will be using in the next lesson. It is the natural language of calculus, meaning when you take calculus, you use a lot of applications of E, and you'll use a graph of e to the x, and you're going to find it has this unique property that no other function in mathematics has. And so what that does, it makes math computations a lot more simple if you use E. So a lot of mathematicians consider E to be this beautiful number that saves us a ton of work because of all the theory that went behind defining it, courtesy of Euler. And it actually pops up into other mathematical formulas. So if you Google Euler's identity, you'll see E being used in that formula. It's one of the formulas he's most famous for. If you don't know this guy, he is the one that's responsible for you having an Apple product. So if you have an Apple product, you wouldn't have it if it weren't for this guy. This is Steve Wozniak. Right? He's one of the co-founders of Apple. He actually invented Apple II back around 1980, and he was able to use that to find 116,000 decimal places of e. That's pretty amazing. So I know I gave you guys a lot of history, and that's totally fine. I'm not going to give you a history test, but here are the things I do want you to take away from this. 1, e is very special, just like pi is special. E is definitely irrational, just like pi. E is the limit, so E is that visualization of that maximum number that would be in your bank account after n intervals, or n times the bank pays you. Another name for E is the natural number, or Euler's number, so they both mean the same thing. And you have to use E when we use natural logarithms, next topic, so that will come up a lot. And then it's good to know roughly what E is, so it's about 2.718. Just like pi is about 3.14, but we know that's not concrete, that's not the official value, it goes on forever, it's not that simple.